Hello everyone, I am Vignesh Gurumurthy. I am a TA for this course Drone Systems and Control, and in this lecture we will be taking a look at eigenvalues and eigenvectors and their significance in drone controls. The objective of this lecture is going to be defining what eigenvalues and eigenvectors are for a matrix, understand the geometric interpretations of these eigenvalues and eigenvectors, and we will then derive and solve what is called a characteristic equation for a given square matrix. Then we will look at some examples to see how we can compute these eigenvectors and eigenvalues, and finally we will connect them with controls and recognize the roles of eigenvalues and eigenvectors, especially in matrix diagonalization. Now let us start. What exactly is an eigenvalue of a matrix? It is a special set of scalars associated with a linear system of equations, and as we know, any linear system of equations can be used or described by a matrix A, and these eigenvalues are called characteristic values or roots. They are the other names for these eigenvalues. So now let us consider a linear transformation represented by this matrix A. If there exists a vector V, a non-zero vector V in the space n-dimensional space Rn such that AV equals lambda V is satisfied, then this lambda is called the eigenvalue and this V is called the eigenvector. Now what exactly is a characteristic equation? If you rearrange this entire equation, you get AV minus lambda V equals 0, where A is a non-zero matrix and these vectors V, as we saw earlier, are called the eigenvectors and lambda are the eigenvalues. These eigenvalues, what they do is they just stretch the eigenvector. When you apply a transformation, let us say A, to any vector V, it gets rotated usually, but eigenvectors are special vectors which maintain their direction, they do not get rotated. Now let us look at it in a geometrical way. Consider this vector V. If you apply a transformation, let us say A, usually the vector gets rotated, its direction gets changed, that is what I mean by rotated. However, if V is an eigenvector of A, then the direction either stays the same or it goes in the opposite direction. Basically V would just simply get multiplied by a scalar value and nothing else, and this is just an example in the 2D space. Notice that the eigenvectors are not rotated, they are only scaled either in the same direction or in the exact opposite direction, and the only change is in magnitude. Now let us look at a very simple example where we have a system described by A, a linear transformation A, and there are 3 cases here where lambda is greater than 1, and we can guess that if we have a vector V like this and lambda let us say is 2, let us call this case 1, all that will happen is the vector will just get extended, nothing else. Now if you look at the second case where lambda exists between 0 and 1, all that is going to happen is, if this is the initial vector V, the new vector will just be this part, it will just get halved. This is for lambda is half, and for the third case where lambda is less than 0, the direction gets reverted. So the vector V goes in the opposite direction. Now this is lambda V, and the scaling is dependent on the magnitude of lambda. Now let us say we have a matrix A and we are given a vector V. Now our goal is to verify whether V is an eigenvector of A, and to do that we compute AV, which is A times V, and we get 8 4, and if we take out 4 we get 2 1 as the vector, which is nothing but v itself. So if you notice, this is of the form AV equals lambda v, where v is 2 1 and lambda is 4. So we have verified that v is indeed an eigenvector of A corresponding to the eigenvalue 4. Now let us take a look at what significance eigenvalues hold and how we can find them. First off, let us consider AV. Let us write them in this form as a matrix equation. The equivalent homogeneous system is nothing but A minus lambda IV, which we get from AV minus lambda V equals 0. So if we take V common outside on the right hand side, we would get A minus lambda IV equals 0. That is how we get this. One important thing to note is that eigenvalues and eigenvectors exist only for square matrices. Only for square matrices. Now let us talk about characteristic equation. This holds a lot of significance in finding the eigenvalues and eigenvectors of a matrix. The characteristic equation is an equation where the characteristic polynomial is equated to 0. So simply put, this determinant of A minus lambda I is called the characteristic polynomial, and if we equate it to 0, this entire equation is called the characteristic equation, and this is used to find the eigenvalues of matrix A. Now here A is again a square matrix and I is the identity matrix, det denotes the determinant. Solving this, we will get the eigenvalues of A. And how did we get here? Remember, we had this equation AV equals lambda V, and we rearrange it to get this equation. This equation, this system will have a non-trivial solution, meaning a non-zero solution for vector V if this condition is satisfied, if the characteristic polynomial is equal to 0, and that will happen when these lambda values are equal to the eigenvalues of the matrix A. And this characteristic equation basically arises as the condition under which non-zero solutions exist. Let us take another example. Consider this matrix A, a 3 by 3 matrix. If we compute lambda I minus A, we will get this form. The determinant of this would look like this. This is basically the characteristic equation of A. Note that you can either use A minus lambda I, or you can use lambda I minus A only when you are writing the characteristic equation, because it is going to be equal to 0. Otherwise, in general, this will not be true. This equality will not hold if not equal to 0. So we can write this because we are equating them to 0, and from here we can easily tell that the solutions are going to be lambda equals minus 1, lambda equals minus 2 and lambda equals minus 3, because if you substitute any one of those values, this term will equate to 0. And now let us take a look at diagonalization. So what you see here is called the companion matrix form. And this is called the Vandermonde matrix. Now let us say we have a square matrix A in this form, and we know that it has distinct eigenvalues. we define something called a transformation, where the transformation we call it P. It is a linear transformation such that x equals Pz. The beauty of this transformation is that if we take P inverse AP, we end up with a matrix where only the diagonal elements are non-zero. We end up with a diagonal matrix. So why is this useful? Now that is a very interesting question. It comes up when we are trying to take the powers of a matrix. We will get into that soon. Now with some repeated eigenvalues, let us say, if what do we do if we have repeated eigenvalues? The previous case was true if we had distinct eigenvalues. If we had repeated eigenvalues, we have a different transformation matrix. Again, notice that this is still in the companion form. So this transformation matrix will work only if the matrix is in companion form, and if we do P inverse AP, we end up with this matrix. Notice that if we have repeated roots, we will have non-zero elements in the non-diagonal parts of the matrix. Earlier when we had fully distinct roots, we only had non-zero elements in the diagonal. However, now we have non-zero elements not in the diagonal as well. Now let us just try to quickly connect how this diagonalization is going to play a role in controls. In the upcoming lectures, you will look at the state space representation of a control system, of a system in general. And now let this be the representation of a LTI system. We are concerned about this matrix A. If we apply the transform for x equal to Pz, you can notice that Pz dot is APz plus BU. How did we get here? X equals Pz, so x dot equals Pz dot, because P is just a linear transformation. And if we pre-multiply the entire equation by P inverse, we will get Z dot equals P inverse AP Z plus P inverse BU. And remember, if A had distinct eigenvalues, then this P inverse AP would just be a diagonal matrix, and this will play a very important role when you are trying to find the next states of a matrix, the next states of a system. And the output equation eventually becomes y equals Cpz plus du. Now let us talk about the invariance of eigenvalues. So what happens to the eigenvalues of a matrix if you do this transformation? So remember, we transformed this matrix by making P inverse AP. What happens to the eigenvalues of A after it gets transformed? So are the eigenvalues same, or do they change? How do they change? Now let us take a look at the eigenvalues of P inverse AP. To find the eigenvalues, as you remember, we look at the characteristic equation lambda I minus whatever matrix you need to find the eigenvalues of. Here in this case we want P inverse AP, and we equate them to 0. This is how we find. Now let us just consider this part, this polynomial lambda determinant of lambda I minus P inverse AP. We can write identity matrix as P inverse P, because this is the same as I. If we rearrange this, if we take the P inverse common to the left and the matrix P common to the right, we end up with P inverse lambda I minus AP, and we can split the determinants again. Since determinants are just scalar values, you can rearrange these three terms however we want. So we end up with P inverse AP lambda I minus A, and note that again we can combine these determinants, so which will just be determinant of P inverse P, and this is nothing but I, and the determinant of I is always 1. Hence we obtain lambda I minus A. So this is what we remain. So what this means is the determinant does not change. The determinants do not change, and not only that, the characteristic polynomial itself does not change, which means the eigenvalues are the same, they do not change. Let us quickly look at another example to understand how to find the eigenvalues and eigenvectors of a given matrix. Let us consider this 3 by 3 matrix A. To find the eigenvalues, we find the characteristic polynomial and equate it to 0. So, we have determinant of the matrix equal to 0, and if you expand it and find the determinant, you will get this equation. This is the characteristic equation for of A, and the roots of the above equation you can find them to be 0.5, 0.5 and 1. Now we have a situation, we have two eigenvalues which are repeating. What we are trying to find out next is, are the eigenspaces. Eigenspaces are nothing but eigenspace is nothing but the space spanned by the eigenvectors. We are going to call the vector x here in this example, but it is the same as the v that we have been seeing in the previous slides. And now we know this is how it is going to look like. See, this is how the equation looks like. A minus lambda I this is what the system looks like now. A minus lambda I times x equals 0, where x is a column vector. We expand this and we multiply it out. If we substitute lambda equals 0.5 in that equation and solve the equations system of equations, we will get two vectors 1 0 minus 1 and 0 1 0. These form the basis for the eigenspace corresponding to the eigenvalue lambda equals 0.5. So, now we have two linearly independent eigenvectors corresponding to 0.5 lambda. This may not always be the case, you might not be able to find two linearly independent eigenvectors for lambda equals 0.5, but in this example it is possible. And for the other case, when lambda equals 1, we substitute lambda equals 1 in that equation, and if we solve that equation we will get another eigenvector which is 1 minus 0.5 minus 0.5, and this is the basis for the eigenspace spanned by the eigenvalue for the eigenvalue lambda equals 1. So, why are these important and how do these play a role in controls? The main point here is they help understand system behavior. In differential equations and dynamic systems, they help determine stability, oscillations and growth or decay rates. So, one important aspect that we will be looking at when we are looking at drone controls is matrix powers and exponentials. These will be essential in knowing how the system is going to behave in the future. However, to do that we will need to compute a power n or e power at, and these calculations become much more simplified if we can transform these matrices, and to do these transformations we need to understand both eigenvalues and eigenvectors. That was the entire purpose of this lecture. If a matrix is diagonalizable, we can write it as A equals PD P inverse, because remember P inverse A P gave us a diagonal matrix D. So we just pre-multiply by P on both sides and post-multiply by P inverse. We will end up with A equals P dP inverse. That's how we got here. And this simplifies the computations of matrix power and exponentials, because if you remember, if we have, let's say, a diagonal matrix lambda 1 lambda 2, and we want to take the a power 3 of this, it will just be simply lambda 1 cubed and lambda 2 cubed and nothing else. So to summarize, we saw how eigenvalues and eigenvectors describe linear transformations and how eigenvalues only scale and preserve their direction, how a characteristic equation is solved to find the eigenvalues, and once we know the eigenvectors we saw how to compute once we know the eigenvalues we saw how to compute the eigenvectors. Then we took a look at we also took a look at the geometric interpretation. Eigenvectors maintain the direction and eigenvalues represent how much they are stretched. And finally, the matrix is, if a matrix is diagonalizable, it means it has linearly independent eigenvectors, only then it is diagonalizable. So we have some reading materials for this lecture. You can take a look at Introduction to Linear Algebra to better understand how to compute eigenvalues and eigenvectors. And you can also take a look at Modern Control Systems by Dorff and Bishop. This will give you a better idea of how we are going to use diagonalization and where it is applicable in controls. Thank you.